Hello, everyone. In this video, we're going to talk about data visualization and graphics using the GG2 plot or GG2 package in R. And in the event or in the spirit of data visualization, I thought it'd be necessary to show a graph of how much we think that we know about R or programming in general, and then how that attributes to how our skill level improves over time, where you can see by some of the fun graphics on this particular plot where as time goes on, we might think we know more about programming. We might think we starting to master things. We have a bunch of setbacks, then we start getting up, then we have more setbacks. I very much just encourage you to stick with it. It gets easier and easier over time the more and more practice that you get with it. I am very convinced that in something like programming, it just takes repetition, repetition, and repetition, and understanding what code you're actually using. And over time, you'll get a lot more comfortable with it, and you'll be able to do a lot of very very cool things with the data as you learn more. So, what is the motivation of building graphics for our data purposes? And that's to visualize, right? That's what are graphics useful for? They're useful for data cleaning. They're useful for exploring data structure. They're useful for communicating information that might not be visible just to the naked eye by looking at some sort of spreadsheet, right? And so visualization offers an alternative way of communicating numbers, right? Just by looking at some sort of spreadsheet we had talked about last week, just by looking at a spreadsheet, I can't tell what some of these trends are, right? By looking at a chart that's going to show me a legend of what kind of variables I have, color coded to what variables I'm trying to or what variables I'm actually looking at, and then trying to find a relationship between those variables. Visualizations and graphics do a great job of telling us things that we might not be able to see. We might not be able to see otherwise just by looking at our data. And so let's take a look at an example of a table and a list versus a chart and a graph, right? So just by looking at this table here, right, I know that I have variables called the sepal length, the sepal width, the petal length, and the petal width, and then the species. This comes from the Iris data set that's already preloaded into R. And so you can take a look at this yourself if you would like to as well. But just know that this is a data set of flowers, of different species of flowers, and comparing their sepal and petal lengths and widths. And so, what are we trying to look at here? Let's try to find some sort of trend. Let's try to find some sort of relationship between our variables that we have here. Okay, so let's say that I wanted to see what species had the longest petal length or something like that, right? And just by looking at the numbers, I can maybe say, maybe the versicolor species, or maybe the Virginica species has the largest length. Or let's even transition over to sepal width. Okay, just by looking at these numbers, I might not be able to see, where these numbers would actually show up on a chart, right? I just know that they are very, very similar, and maybe there is an underlying relationship that I need to explore. But I just cannot see that with my naked eye just by looking at this table and these list of variables. Okay, but if I decided to go ahead and try to explore some sort of relationship, we could look at, for example, let's plot the sepal length against the sepal width, and then color by our species, or try to separate it out by our species, just to give us some sort of relationship, some sort of information about the data set that we might not be able to see just by looking at the table. And now that we take a look at this visualization, we can see that there are some relationships between these two variables that we may not have been able to see just with our naked eye, right? It's pretty clear to see that after we split out by species, we can see that the Setosa species of flowers has a lot higher width than the rest of them, right? And you can see also the Virginica species of flower has a lot longer sepal length than the rest of them, right? Visualizations can aid communication and make data very easy to perceive. We had talked about last week where we wanted to take a look at the data even before we got into any sort of data exploration when we were looking at it. And this basic visualization is another thing that we should do right away to see if we can try to answer some questions or try to see some sort of relationship as soon as we get our data to try to learn more about what our data is actually trying to tell us, right? So now we can process and understand that relationship and have that in the back of our minds as we keep on going with the rest of our data or with the rest of our data analysis. Okay, so just kind of getting into some types of graphs. Go ahead and take a look at the Data Viz project and data visualization catalog just to kind of see what is actually out there and what kinds of graphs you can create using R. And some some beginner visualizations might include your one variable graphs, your bar chart, your pie chart, where you might have your continuous ones or with your continuous variables, your stem and leaf plots, your box and whisker plots, your histograms. Maybe you're looking at two variables. That's going to be your scatter plots. We just looked at one. Maybe some maps as well. But it's useful to know all the different types of graphs that are out there just so we understand what we can accomplish and what we can actually utilize to convey that information that we have at hand. Again, I implore you to take a look at the DataViz project and data visualization catalog. It has a lot of really, really great, useful tools in there for you. So some intermediate graphs, you might see some parallel coordinate plots, some mosaic plots, some radar charts, some heat maps. I talked a little bit where I like to use a lot of sports references. We might see some heat maps with that for something like baseball. And also some advanced graphs, you might see some density plots, some violin plots, some social network plots. But for this class, we're going to focus a lot on the beginner plots and trying to make them as pristine as possible, and maybe look at uh, converting them even to something like an interactive graph as well, interactive plot as well. So let's take a look at the grammar of graphics for utilizing the ggplot2 package. So what is the grammar of graphics? It's developed by Leland Wilkinson. It's a set of grammatical rules for creating perceivable graphs, right? So it's similar to something like constructing a sentence. We need to have a grammar of graphics as well, so that we are creating something that's actually going to make sense, that R can read and will be able to spit it out correctly, and also something that's going to make sense as we are building and creating this graph ourselves. So rather than thinking about a limited set of graphs, think about graphical forms. Charts are instances of much more general objects. An abstraction, which makes thinking, reasoning, communicating much easier. So going down the line, again, we have our source, we have our data, and then us as data analysts, us as people working with that data, we're going to take a look at the variables. We're going to take a look at the algebra. We're going to take a look at the scale, statistics, geometry, coordinates, all these different things, and then put them into some sort of aesthetic that then is going to render as a graphic that we can utilize to communicate information with. So different types of graphs may appear completely distinct, but in actuality share many common elements. So just thinking about these different graphs here, is we can see that we have the same data, but three very different ways of displaying that data. Okay, and so whether you are tasked to, let's say, the task that you have at hand is going to dictate the way in which you are going to display your data, right? So let's say you're trying to do, just trying to show a a difference of, let's say, in this case it's cuts, right? We're going to look at the count, which we're just counting in a data set of diamonds. We can see, if we just wanted to show the difference between the amount of cuts in this diamond data set that we have, right? We can just utilize a basic bar chart, right? And so now I see, I'm fastening out my cut here. I can see my fair, my good, my very good, premium, and ideal. And now I see that I have obviously a lot more ideal cuts than premium or very good or fair. And maybe, let's say I'm shopping for a diamond or something like that, and maybe I'm on a budget, and maybe I need to go and see how many cuts of good I can, or maybe I'm looking for a cut that I can actually afford. Maybe it's good or fair, and maybe I just want to see how many of those cuts are actually out there, and how quick do I need to act to go buy one of these fair cuts or something like that. Just sort of an example there. But as you can see, this same exact data can be shown over here in this fill bar, where maybe it's not exactly as clear to me that the ideal has, over, let's say, 7,000 more count or more amount of cuts than the premium, or there's looks like there's 2,000 more premium than very good. That's not as clear to me, but there might be a specific situation where a fill bar garners, or where a fill bar satisfies the needs that I need to meet. And then the same thing with a pie chart. It's going to be, it's maybe I'm just trying to show, the quantity of which goes where, this goes there, this goes where. But in my opinion, if I'm just looking to see the difference in between the different variables that I have, I'm probably not going to be using these last two. I'm probably going to be using this one. But again, as we think about the problem that we have at hand, the questions that we're trying to answer, different types of graphs are going to satisfy different problems that we're going to solve. Okay, so statistical graphic specifications are expressed in 6 different statements. Okay, data, the set of data operations that create variables from data sets; trans, which are variable transformations; scale, which are scale transformations; chord, a coordinate system; element, graphs, points, and their aesthetic attributes; and then guide, one or more guides, which are going to be our axes and our legends. And you'll see these inside the syntax for a lot of the ggplot graphs that we're going to create. So what are the limitations that we need to think about when we're building our graphs is, grammar tells us what words make up our graphical sentences, but offers no advice on how to write well. It's just plain and simple. Sometimes in ggplot, it's we have to have things in very particular spots, or else it won't work, right? And so maybe I put a part of the syntax where it's supposed to be after the word that I'm trying to use, and it's not going to work as well, and it's going to give me maybe a different graph than I was actually looking for. Grammar is not about good taste, practice, or graphic design. It's just showing essentially the basic data structure, the basic infrastructure on how to build a graph. It's not going to tell us how to build this beautiful graph that we need to present in some sort of project or something like that. So while very useful, the grammar is not at all encompassing. It does not include interactive graphics. I will show in the advanced part of graphics where how we can make these a little bit more interactive and a little bit more user friendly, so that if you're trying to, let's say we're presenting to a lot of different people, they can actually interact with the graphic and actually have a little bit of fun with it. It does not include a few interesting and useful charts. Again, with the grammar, we are just limited to what the ggplot2 package has. Okay, so now actually getting into the syntax and actually looking into the ggplot2 package, which is a layered grammar of graphics. What this means is it's ggplot2 is based off the grammar of graphics, but let's think about this as layering every single part of that grammar on top of each other, right? We're going to start with the data. That's going to be our default. We're going to start with the trans, which is going to be the transformations of our data into what we want it to be. Okay, our elements, which is going to be our layers of data that we're going to build on top of each other to build the infrastructure of what the graph of the graph that we're actually trying to use to convey information. We're going to use a scale and the guide then to, let's say, make our text smaller. Let's say, make change the color of our title or something like that. And the coordinates, the chord, going to be use the coordinate and then the facet options to essentially put the graphs in the exact place that we want them to go. In both grammars, the components are independent, meaning that we can generally change a single component in isolation. So what is a graphic? So ggplot2 uses the idea that you can build every graph with graphical components from 3 resources. The data, which is represented by geomes. You'll see geom a lot when we're using ggplot. That's going to be essentially the start of the syntax for almost every single function that we use. The scales and the coordinate systems, like I said, the scales, that's going to be changing the font of your changing the font of your chart. Maybe that's changing the where it is on your chart. And then plot annotations. Maybe that's changing your circle points to square points. Maybe that's changing your maybe that's getting rid of your grid or something like that. So display values, map variables in the data to visualize properties of the geom, the aesthetics, like size, color, and XY locations. Okay. So like I said, ggplot2 is a layered grammar. Okay. So think of it as starting with the bare bones, which is that graph, that very empty graph, which is going to look something like this. Okay. And then you add another layer on top of it to build the graph that you're trying to build. Okay. So, like I said, a default data set of set mappings of variables to aesthetics. It's going to start exactly with that coordinate system, and then you're going to build on top of each other with some component of that grammar of graphics that we had talked about. Okay. So, what is a layer in ggplot? It determines the physical representation of the data. Okay. So, a plot might have many layers. Okay. A physical representation of the data, meaning, again, I start with that chart. That's one layer. Maybe I want to show the legend of what variables I'm looking at. That's another layer. Maybe I'm trying to show the XY axis. That's going to be another layer. Okay. Usually all the layers on the plot have something in common, i.e., different views of the same data. All right. A layer can be composed of 4 different parts: data and aesthetic mapping, a statistical transformation, a geometric object, and a position adjustment. Okay, and we'll get into these once we start building our graphs. Okay, so some specifications. A plot consists of several mostly independent specifications. All right. And so again, now I'm thinking about just building the infrastructure of my graph. This is all in the syntax, and you'll see these words come up and up again when we're building our plots. Okay. So aesthetics. Those are the links between data variables and graphical features. Okay. That's going to be your positions, your colors, your shapes, and your sizes. Okay. Layers. That's going to be geometric elements, your points, the lines you create on your graphs, the rectangles, your text. Okay. Transformations. Transformations specify a functional link between the data and the displayed information. Okay, that's going to be your identity, your count, your bins, your density, your regression. Okay, transformations act on the variables themselves to change the layout of the graph that you're trying to build. Okay, scales. Scales map values into data space to values in the aesthetic space. Okay, that's changing. Like I said, that's going to be changing the size of your text or something like that. Scales change the coordinate space of an aesthetic, but don't change the underlying value. Okay, so they change at the visual level, but again, not the mathematical level. Think about something like the size of your exact text or something like that. Okay, so coordinate system. Okay, that's going to be your either polar or Cartesian. Some of you that may be in math might think about the Calc 3 when you had to change some of your things to the polar coordinates. That's just an example of some of the things that you can look at in the coordinate system. You're not going to be changing in this class. You're not going to be changing from the Cartesian to polar. It's going to be your basic, x axis, y axis, looking in that first quadrant. Okay, faceting. Faceting allows you to split plots by other variables to produce many subplots. This is very, very important. You'll see in a little bit. This is very, very important when we have a lot of different variables and we have a lot of observations. All right. So if I'm thinking about that and trying to graph some sort of scatter plot or something like that, I have a bunch of different points that are probably going to overlap all over the place. Okay. So if I can facet or essentially take out each different variable by themselves and create a subplot of just that variable, that's going to be very, very helpful to me in trying to understand what's going on within that one variable. And theme, formatting items such as background color, fonts, and margins. Okay. So again, let's just take a look at this. Let's take a look at those 3 graphs that we saw earlier, and just kind of look at what the aesthetic and those geoms and the coordinates might be. Again, we're looking at that data, or that diamonds data. Our aesthetic, our x equals our cut, our y equals our count, and our filling of our bars is going to be by cut. It's going to be a bar graph, so our geom is going to be bar. And then, of course, this is in the Cartesian coordinate. Same thing here. So x equals 1, instead, we're not actually looking at specifically by cut. We're just looking at one bar graph. So y equals count, same thing. Fill equals cut, same thing. But our geom this time, instead of bar, is going to be fill bar. Okay. And other types of geoms might be geom point, which is going to be our our scatter plots. Geom histograms is going to be another type of bar graph. It's going to be our histograms, among others. And then our coordinates again are going to be Cartesian. Okay, so in this one, we actually had the same exact plot, but except our coordinates were polar, which again is going to change that into a circle or a pie graph here. Okay, so again, ggplot is just here's a fun little graphic about how we can build different things using our ggplot. We're just trying to build very good visual graphics, and in my opinion, the ggplot2 package is the best way to do that in R. Okay, so let's make our first figure using the ggplot2 package. Okay, so the R package in the data set, we're going to use that same exact diamonds data. Again, we are looking at kind of adopting that same principle as we talked about last week. We're introduced to a new data set. Let's take a look at that data and see what we're actually working with here. Right. So we're going to take that the head, which is going to give us the first 6 observations of what we are looking at with all of the different variables. So head of diamonds, I have a variable of carat, which is obviously how big the diamond is, the cut, the color, the clarity, the depth, the table, the price, and then XYZ, and then XYZ variables. Okay, so let's begin with the data. ggplot data equals diamonds. Awesome, we have something to build our base off of. We are now starting with our data. Boom, that is our first layer. Okay, so let's make some aesthetics with it. Okay, so now let's do AES. This is how we're exactly how we're going to code it. Okay, let's build another layer. Let's build that graph. Let's build that first quadrant. Okay, AES, X equals carat, Y equals price. I want to look at the relationship between carat and price. I'm just trying to go out and find some sort of relationship. Maybe I have a hypothesis that the bigger the diamond, the higher the price, which is probably going to be accurate. But let's just try to look at that relationship. I want to label that as X on my X axis going to be carat, Y axis equals price. And now let's look at geom point. Okay, so the diamonds data set obviously has a ton of different observations to be looking at here. Okay, and so if I just did a regular geom point, which is a scatter plot of all of my data, I'm going to get something that looks like this. Okay, and so now you can obviously see that there looks like there's some sort of positive linear relationship that goes up to 1, and then we're just kind of, it's just kind of a crapshoot after that. We don't really know what's going on. Okay, so looking at the data as a whole, we kind of really don't know what's going on. We can see that, generally it looks like as we get into the bigger carats, the higher the price is going to be, but not necessarily. Let's try to see if we can go even deeper, and try to look at each type of, let's say, cut by themselves. Okay, so now I'm going to put an aesthetic on the points. Okay, so the aesthetic that went on the ggplot first, that's going to be the aesthetic of the graph in general. Okay, and now I am appointing an aesthetic to the points themselves. All right, so I'm going to color by cut. And so obviously you can see over here now that we have a legend that's going to give us cut, labeled by fair, good, very good, premium, and ideal. It's still not super clear. It's kind of a jumbled mess, like I was talking about earlier. Maybe you could talk about how these the fair cut of diamonds, they as a collective, they're going to be cheaper as the good, very good, and premium, and ideal, which again makes sense to us. But just taking a look at something like that's going to be very valuable information to somebody that might not have known that. Okay, so let's go even farther. Right, let's smooth this out. Let's see what kind of trend we're working with, and let's see what kind of trend we might be seeing into the future. Okay, so geom smooth essentially appoints a line of best fit for our data. All right, so you can see this blue line is going about right in between the middle of every single one of these, and then ends with a confidence interval. That's what the shade is. a confidence interval of where the data would most likely lie as it moves on into the it moves on to the right with carrots as carrots gets more as carrots gets it gets larger. Okay, so why do we see a confidence interval here but not here, right? And the answer to that question is that we don't have nearly as much data up here as we do down here. So we're making our best prediction of line of best fit going forward after we hit this huge lump sum of data. Okay. So again, this still isn't telling me a ton. So let's go even farther. I can again append an aesthetic for that smooth, right? And so now let's go out by each single cut of diamond, right? So now let's look at the line of best fit for each single cut of diamond, right? So I can see that this red one is following a lot lower than the rest of them, all the way down here. But what's something that might be very, very useful and something that we did not see earlier is that the dark blue, the ideal cuts, looks like they have almost an inverse relationship as it goes on with carrot. That's a pretty interesting finding if you would ask me, right? Where you can see that good is still on an upward trajectory. Very good still on an upward trajectory, and premium still on an upward trajectory, but ideal, interestingly enough, has a downward trajectory as it gets larger, as carrots gets larger. Again, what that might attribute to, I'm thinking that now I just don't have enough data to actually support what's going on here. I have a bunch of ideals up in here, but as I get higher and higher in carrots, I just don't have as much data. And so being able to say and being able to claim that, as I increase the carrot, the price of ideal diamonds are going to go down. I just can't say with say with confidence that the truth that that's the truth. But based on our data, you might be able to say that. Okay, so again, let's keep going. Let's keep going and make this even. Let's make this even better than it was before. Okay, so we can append coordinate transformations to be specified, and let's change the law or let's change the scale of the data that we're looking at. Okay, so now we're changing it into a log base 10. So now the numbers aren't, or now the prices aren't specifically on a 0 to whatever they were, 0 to 50 or 0 to 20,000. Now they're on to 300,000. Okay. And so now look at this. This is going to completely change the way we interpret this graph, right? So now that we've appended this transformation, now we can see that, just about every single one of our graphs have that upward trajectory. Okay. These are going to, every single one of these transformations, the aesthetics, every single one of these are going to change the way that we interpret our graphs. It's only going to add more and more information as we are conveying information to other people. Okay, again, one more time. Let's go ahead and facet the variables. Okay, so we're going to facet wrap, which means essentially just wrap that graph on all the same line, essentially. But now I can take out from that graph, from that ugly looking graph, I can take out every single individualized variable. All right. So now I see fair. Now I see good. I see very good. A premium, ideal. Now the readability of this graph is a lot more tailored towards somebody that might not have super statistical working knowledge, right? So if I'm let's say a CEO of a diamond company, now I can actually read this graph where on this one I might have just said, hey, I don't really know what's going on here. It just looks like a jumbled mess. Now I can actually take it out by individualized cut. Now I can see the trends. I can see how the data is actually wrapping. I can actually see the way the data is behaving, and that's going to only benefit. That's only going to benefit me as a data as a data analyst in conveying information and conveying important things about the data that we have at hand. Okay, so that covers some of the basics and how we kind of build out a ggplot graphic. And so let's just kind of buzz on into more and more or more basics about building graphs. Okay, we talked about why data visualization is important, which is exploratory data analysis. That's kind of the focal point of this class, is learning this programming so that we can perform exploratory data analysis. So let's take a look at some sort of example, which is the Anscombe's quartet exercise. Okay, so what this entails is that we have four different data points that are almost identical simple statistical properties that appear very different when graphed. Okay, we'll take a look at the data here in a little bit. But this demonstrates the importance of graphing data before we analyze it. Okay, so if I rely just on the summary statistics, we talked about the summary statistics last week, where that's your mean, your mode, your median, your max, your mins, all that good stuff. Um, so if I rely just on that, just on those statistical functions, I'm going to have a tough time producing reliable interpretations of the data. All right. So what I mean by this is let's take a look at these four different data sets. Okay. So let's just kind of use our eyeballs to look at the different numbers that we're actually looking at here. Where yeah, we have different x values. All of these looks like they have the same x values but different y values. Okay. So obviously very different data sets, but if we take a look at summary statistics, they're all the same. All right. And so if I'm trying to make decisions, if I'm trying to make assumptions about the data by looking and using my eyes or using the summary statistics, right, it's going to, in this case, I'm going to be very, very wrong in saying that, well, they're all the same data, right? So let's take a look at, we have our mean of 9, standard deviation, standard deviation of y, correlation. Let's just take a look and graph the x variable against the y variable and see what I mean by how wrong we can be if we relied solely on other things other than graphics. Okay, and so let's take a look at the scatter plot, right? So this is just very, very, very different if you took a look at a graph than just the summary statistics, right? So taking a look at one, it's got your basic, positive linear relationship between x and y. X and y here look like they have a parabolic shape, right? And so this one looks like it's a straight line except for one. On this one, it's a vertical line except for one, right? And so this is just emphasizing the importance of graphics and doing graphics well to make sure that we are getting all we can out of the data that we have. We are interpreting our data in the right and correct ways when we're looking at data analysis. Okay, so before it's possible to talk about graphical grammar, it's important to know the type and format of the data that we're working with, right? And we had taken a look last week on how we can actually observe what kind of variable types that we're looking at as well. But why is that? Okay, if the data contains all the information you're trying to convey, right? The appropriate graphical techniques depend on what kind of data that you're working with, right? I had talked about earlier that we are looking, or I had talked about earlier with the different data types that we had. We could have um, mu- or continuous or discrete. We could have had binomial, multinomial, polynomial type data. So working with R and ggplot is much easier if the data you use is in the right shape. Okay. Oh, so great. So like I said, so we have our quantitative and also our qualitative data levels of measurement. Okay. So we have continuous variables, which is our height, our weight. We have discrete, which is a solidified number, age in years, right? Our qualitative, okay, which is our nominal, which is our categories, right? So when we talked about the flower data set, we had categories, which were our species of flowers. Okay, so categories have no meaningful order, and also something like colors, something like types of flower species, something like that. Okay, so ordinal. Okay, categories have order, but no meaningful distance between categories, right? 5-star ratings, divisions in athletics, conferences, seedings, all that good stuff, right? We need to understand, we need to know what kind of data that we're looking at before we actually do some graphics, because that's going to depend on what we're graphing and how we're going to build those graphics. Okay, dimensionality, form, and type. Your dimensions: univariate, which is one variable, like I said, bivariate, two variables, multivariate, which is 2 plus variables, We have different forms, which are traditional and aggregated. Traditional might be your one at a time, where your aggregated is where, let's say, we're getting one number for all of the type or all of the Setosa flower species or something like that. Types are count, word frequencies, sports statistics, time series, spatials, time to events, survival, reliability, categorical. There are so many different data types um, that are all going to have some sort of impact on on the graphics that we create. Okay. So, how do we look at this? We can explore relationships between these different variable types, which is so. For an example, we can for with exploring continuous versus continuous, you might look at a scatter plot or a line plot. Continuous versus categorical, you might look at a box plot, a dot chart, multiple density chart, a violin plot. Categorical versus categorical, a mosaic plot, side by side bar plots, multi-dimensional. You get the idea. Again, take a look at the data viz project, the data visualization catalog. Take a look at the textbooks. They have very, very great examples on how we can understand some of these relationships and how we are going to create graphics based on what we're trying to figure out. Okay. So before we take a look at really diving super, super far into graphics, is we need to understand how we're going to format our data and the different formats of our data and how they're going to impact the graphic that we create. Okay. This is going to be a tidy data discussion. We'll talk about this a lot more in detail in a couple weeks, but let's just take a look at it and give a brief introduction for it. Okay. So working with R and ggplot is much easier again if the data you use is in the right shape. Unlike base graphics, ggplot works with data frames and not individualized vectors. ggplot expects your data to be in a particular sort of shape, which is in a tidy data format. Okay, so let's take a look at this. Same data, but different layouts. All right, let's look at option one. We have our name, we have our treatment, we have our treatment A, treatment B. We have you know, our name attributed to both treatment A and treatment B. That's fine. We can read that. That's great. Option two, essentially the same thing, but now treatment A is over on the left. Now we're giving, our column names are going to be our column names are going to be the individualized names that we have. And then option three, where we have our name, our treatment, and then our measurement that's going to come out of that. And now let's think about which way we actually want our data to be in when we're trying to create a graphic. Okay, so wide format versus long format. Right, so some variables are spread out across columns. Right, so typically this uses less space to display. And if I were going to give you a table, this is probably how I would give you that data and how I would present this data to you. Far less repetition of variables and row elements. So you're going to have a lot less data. It's just going to be the way it is. Okay, but let's take a look at long format. Each variable is a column, right? So taking a look back here, each variable is a column. So our name variable, our treatment variable, and our measurement. Okay, each observation is a row. Okay, so I'm not creating, like option one, I'm not taking a look at John Smith and both their treatment A and treatment B is in one row. I'm taking a look at just their treatment A and then their measurement, just their treatment B and then the measurement. Okay, and it is likely not the data's most compact form. All right. Okay. Um, but this is how we tidy our data. This is how we get our data into a correct format so that we can easily and effectively create graphics to depict the information that we want to find out. Okay. And so you guessed it, option three is the tidiest data that we can get to. This is what we're usually trying to get to once we're actually trying to clean our data. So we want to make sure that each variable is a column, each observation is a row, and each one, and we call those observational units. So each observational unit forms that table. Okay. So now thinking about messy data. If you've used a data set before, you've probably seen some sort of aspect of messy data. Okay. And so five main ways tables of data tend not to be tidy is when we have column headers are values and not variable names. Okay. Multiple variables are stored in one column. Variables are stored in both rows and columns. Multiple types of observational units are stored in the same table. A single observational unit is stored in multiple tables. Again, we will talk about what this means on a deeper level in a couple weeks when we talk about data manipulation. But it is very, very important to understand how and what makes messy data and how we can get there to make it so that the data is in a format that we can utilize for graphics. Okay, so take take a let's just take a look at an example here. This data, this French fries data. Again, we're gonna take a look at what we're working with here. So let's do the head function of that French fries data. I see that I have time, treatment, subject, rep, potato, buttery, grassy, rancid, painty. Sounds like some sort of different variable type, which is fine. But we're in wide format, right? We have variables as our column names, which is fine for data presentation, right? This is very easily readable. But if I'm trying to make it some sort of uh, if I'm trying to make it some sort of way that's going to be easy for me to create a good looking graph, we're going to need it to put it into long format. Okay. And how we do that is the pivot longer function. Okay. So this is the specific syntax for the pivot longer function where I can see over here, I want to look at just these five because these are my different variable types. I'm going to look at the columns of potato to painty. I want to change those names to variable. It's going to reflect that down here. And I want to change those values to actually have a column name of value. Okay. Now let's take a look at what this data actually looks like now. Now I have time, treatment, subject, rep. Now I actually have a variable and a value that attributes to that, right? So now I have each observation to be a row, where earlier I did not, right? I had a row as each repetition, which is not what I wanted it to have. I want each observation to be a row, right? So at time one, at treatment one, at subject three, at repetition one, I have the variable of potato. Its value was 2.9, right? And so now if I go down the line, if I wanted to just go keep going with the potato variable, I have time of one, treatment of one, subject of three, repetition of two now. It's a completely different observation, but now it's their second repetition, potato, and then value. Okay. Again, and now take a look and just try to utilize this pivot longer function just to get a little bit of practice. Again, we'll talk about it next week or in a couple weeks as well about how to tidy our data. But it's very, very important as we build our basic graphs that we need to get our data into its own specific format for us to build these good looking graphs. Okay? So now let's actually build these plots that we have just now set up. Okay. Again, what's the underlying theory? What's our graphic? We have seen this before. You use the idea that you can build a graph you can build every graph from the same component, the data, the coordinate system, and genomes. We talked about this earlier. Let's keep going. Now, how to build a graph? We had seen this a little bit with the syntax of the basic graph that we built. Um, you know, this is going to serve as the template of how we're going to build our graphs using the ggplot2 package. Okay, so ggplot data equals our data plus whatever geom function that we're doing, right? Now we're going to use our aesthetic to whatever function that we're doing. Maybe we need to create an aesthetic on the ggplot, stat equals stat, position, facet, scale, theme, coordinate function. We'll dive into these as we get and as we follow along here with actually building our graph. Okay, so this will begin. The ggplot, the data starting with the data, and then the aesthetic. That's going to begin a plot that you can finish by adding layers to. We had talked about this earlier, right? You can add one geom per layer. Okay, so I started with the aesthetic of just the looking at city by highway and the MPG data in the MPG data set, where now I can see I have looking at class, I guess, here in this one. Okay, so I'm looking at the different types of cars that I have and how their highway mile and how their mileage or their highway mileage is. Okay, and so I can add a box plot to this function. And now I can see for this two-seater, my data ranges from anywhere from looks like, 23 to 26, which makes sense. A compact car is going to reach anywhere from 25 to even as high as, 44. Midsize going to hover right in that 23 to 33 area. Minivan, obviously, it's not going to have as much. Pickup, same thing. Subcompact, you get the idea. SUV, same thing. Oops. Okay, and so now let's add this jitter function to our geom box plot function. Okay, again, it's another layer that we are adding onto our already created layer of graphics. Okay, so I started with this, which was just this basic function here. I added a box plot, so now I'm adding the box plots to my specific variables. And now this geom jitter actually adds the specific data points to my graphic. Okay. It's now taking a look at, this right here. I can actually see that there's a two-seater that has, our 26 miles an hour. I can actually see where this data point actually is. It's right around, yeah, you get the idea. And you can actually see the essential distribution of my data points on the specific box plot. Okay. Again, you might not actually even need this function at some point, but it's good to understand how we can build these how we can build these different graphics to tailor to the task that we might have at hand. Okay, so what is a geom? Right, we talked about this earlier in ggplot2. We use geom functions to represent our data points and use the aesthetic properties to represent our variables. All right, once our data is formatted, we know what type of variables we are working with. We can then select the correct geom for our visualization. All right, so taking a look at this specific function, right? We in this one we use geom point, but in this one we use geom text, right? Which one makes more sense for us to convey information about our data, right? Probably the geom point, where we're already looking at, we are already splitting it out by class. But to somebody's point, we could do geom text. It's going to show us essentially the same thing, but for readability purposes, we're definitely going to want this specifically correct geom for our visualization because we understand what type of variable that we have, right? And so obviously you can rattle off a bunch of different reasons why this probably isn't the right way. And then you can see, right, we can see a lot more information. We can make a lot more conclusions about our data if we're using the right visualization. And in this case, it's going to be geom point. And again, now we can make the assumption that, our compact cars are going to mostly be in that higher highway mileage or highway miles per gallon. Also, our higher city miles per gallon. Okay. So available geoms. There are a bunch of different geoms that we can create using the ggplot2 package. And again, these are all available on the modules page of our canvas. Um, Again, I encourage you to take a look at some of these and make sure that you understand what types of tools that you have when creating graphics. Okay. So again, what is a layer? We've talked about this. It determines the physical representation of the data, how we're actually portraying that data on our screen. Right. So an alternative method of building layers is using statistics functions. All right. So a stat builds a new variable to plot. All right. Which might be a count or that might be a proportion. Right. That's also on somewhere on our the ggplot cheat sheet as well, where now we have, we might be looking at a density function, we might be looking at a quantile, we might be looking at summary statistics, right? And that's going to change the way we look at our data on the screen, right? That's essentially creating another layer, right? And so if we wanted to do, a stat count instead, which calls a default geom to make a layer of the geom bar. It's the same exact thing. It's just another way of building a layer on our graphics on our chart. is utilizing stats. I implore you to also look at these, stat functions. Okay. One more thing that we need to talk about is faceting. Again, we talked about it earlier and the importance of how we can utilize it. It's a way to extract subsets of our data and place them side by side in graphics, right? So again, we had taken a look at this kind of very close together graph of all of our different types of cars, and now we can essentially take out the specific and individualized variables of cars to see what they actually look like on an individual basis, right? And in a sense, this is probably going to reflect a lot about what our box and whisker plot's going to look like, right? So, we saw in our two-seater, the range only went from 23 to 26. We can see that. With compact, we know we could see from all the way up, or from 23 all the way up to 43. Mid-size, minivan, pickup, subcompact, you get the idea. But understanding what Facet can give you is very, very important for your own readability purposes, and then also for conveying the information that you might need to somebody else for their readability purposes. Okay, so different faceting options that we have are, facet grid, which is going to facet into columns based on B. Just taking a look at this first one. Faceting into columns based on B, facet grid with A is going to facet columns based on A. Facet grid of A and B is going to facet both rows and columns. And then facet wrap wraps the facets into our rectangular layout. We saw that a little bit earlier. You can also set scales to let axis limits vary across facets. Okay, so you can set X and Y axis limits to adjust to individual facets. So let's say, let's say that we are only looking at the compact and, let's say, mid-size cars, right? I'm not going to need any of these things below 20 because I know none of these cars have or have highway mileage below 20. So if I wanted to, I could say, free Y, and I can individualize that to myself, where I can, set the access limits to, let's say, 20 and above, and so for something like that. You can also set a labeler to adjust facet labels. If I wanted to say something different than, what the variables actually were. If I want, let's say, maybe the two-seater wasn't super clear to me, and I can say, let's say it's just individual. Let's say it's just an individual company or something like that. And so the two-seaters were all, I don't know, uh, Pontiacs or something, Pontiac convertibles or something like that. So I could say, for the first one, I could say Pontiac convertible if I wanted to, and create a different, or set a different labeler for my data. Okay, so position adjustments determine how to arrange geoms that would otherwise occupy the same space, right? Dodge, fill, and stack. This is very, very important. Where, let's say, I'm trying to see the difference between three different levels of something that I'm interested in, right? So in this case, Dodge is going to arrange elements side by side, right? Whatever this DRV variable is, right? I have three different variable, or three different trials or something like, or three different, let's say, treatments of this R variable, right? And they're for F and R, right? And so I have three different treatments of P, three different treatments of E, three different treatments of D, right? So the Dodge is going to allow me to see all those different treatments side by side. All right. So with fill, it's kind of the same kind of deal that we saw with the fill bar geome, where now I can see these three different treatments up against each other, and much of my of the how much of the count that actually fills up, right? And so you can see R obviously does not attribute to a whole lot of this R. The RDRV does not attribute to a whole lot of the RFL. And then stack, you could do the same exact thing, where you can actually stack the counts on top of each other. That's all going to be dependent on the position of your geome bar. Okay, so that's position equals blank. Dodge, fill, and stack. I personally utilize the Dodge one a lot, even today still, when I'm trying to compare different levels of the variable I'm looking at. Okay. We talked about jitter, where you can essentially show every single one of the data points from that specific variable, right? So if I did position equals jitter, and now I can see every single data point of the um, force or of the cylinder of our engines. It looks like so our four cylinders. You can see every single data point for those highway mileages. Same with five, same with six, same with eight, and again, and so on, right? So jitter and adds the random noise X and Y. To avoid overplotting, there's also the jitter geom. All right. So coordinate systems. Okay. So these next ones might just be a little bit more supplemental, usually, but I'll point out some of the more important ones that you might actually use. Okay. So chord Cartesian, which is the default Cartesian system, you actually probably won't need to change this a whole lot. Chord fixed, which is a fixed aspect ratio between the x and y units. You probably won't use this a whole lot, but let's say you have um, you had a very specific way and you needed to portray your information. Maybe we need to just stretch this a little bit longer. Maybe we need to shrink it again. Again, maybe you have just a ton of data. Maybe we might stretch this out, and maybe that would have made our um, scatter plots make look a little bit better. Who knows? So chord flip, that flips your Cartesian coordinates on its side. Sometimes this is a little bit easier to show. Let's say for comparing you know, speeds or something like that. And R was, let's say, a pitch speed and count was miles per hour, right? Maybe I wanted to see who threw the fastest. This would be a pretty good idea to flip our coordinates to show a little bit easier. Again, polar coordinates down here, you can make them into map projections. You can make them into a different transformation if we wanted to. These are a little bit more supplemental than some of the graphs that we're going to be looking at, but just wanted to show you more and more options that you might have to, let's say, to tailor to your needs that you might the tailor to your needs that you might need. Okay, maps. So map we so ggplot has a very, very cool functionality with maps. Again, I just want to show you this. We might not do a whole lot of maps, but plotting geospatial data is a common visualization task, but one that requires specialized tools. Okay, so typically the problem can be decomposed into two different problems. We're using one data source to draw a map and then adding the metadata from another information to source that map. Okay, so let's just take a look at an example with Nebraska population, where we have this map data for the counties of Nebraska, and populations of those actual counties, right? So I have two different data sources, and I need one source to create the map, and I won't need one source to visualize the map. Okay, so these counties are going to actually draw the map of Nebraska split out by counties, where the population data is actually going to help me visualize how densely populated each county of Nebraska is. Right? So let's just take a look here. Whoops. Let's take a look here at this code, where it's actually going to show us, right, off of a oops trying to show what this actually going to show. Perfect. Okay. So this geome polygon is actually going to help us create an actual map of Nebraska, which is actually really, really cool. And then the fill of our population is then going to show us how densely populated our counties are going to be. And again, this is a continuous variable. And so it's going to show in this kind of almost like grid like pattern where it's going to go white up to green. But again, just showing you an example of how we can utilize the ggplot2 package to create very, very cool, very cool plots. Okay, so some extensions we have ggforce. which is a little bit, just a different variation of ggplot and how we can actually do some of these different do some of these different graphics. Vernoi, another one that's used a lot of spatial data, and we can actually map elevations, which is pretty cool. ggridges, temperature, ggRepel, patchwork. You can take a look at all these different extensions here at this link. And again, I implore you all to take a look at the textbook, take a look at these links, take a look at your cheat sheets, so that you might be able to master creating beautiful graphics to visualize your data.